Okay, so a very good morning once again, and you're welcome to class. So we pick things from where we stopped last time. So, so far, any question before we begin? Because we'll try to do a lot of in-class activities today. Okay, so in our last class, we introduced computer organization and architecture, and we're able to address a few details. And we're also able to introduce VHDL programming. And I want to believe by now, you've all started getting a little comfortable, programming in VHDL. So any question, please, from what we talked about last time? Do you want us to review any concepts? Feedback, please. Okay. So I'll run through this quickly. I'll introduce this, then we'll go into our in-class presentations. The machine representation of instruction and data. As we already know, everything we've got to do as far as the machine is concerned has to do with our zeros and ones. Okay, so we try to pull that through when we, talked about the architecture. And oftentimes, when we talk about architecture, what comes to mind is the instruction set architecture. And we also have another subgroup, which is the hardware system architecture. Okay, so I'll just more like a recap coming from the architecture perspective. So, and then although we have them in our notes online, and when we talk about the instruction set architecture, then we want to make mention of the instruction set itself. And then we went on to classify computer architecture. I know we've talked about von Neumann, the non-von Neumann architecture, modified Harvard architecture, and the likes. And then then based on the number of processors, we talked about multiprocessor systems and all of that. And in our previous notes, which you already have online, we already made mention of the single instruction stream, single data stream, single instruction stream, multiple data stream, and the likes, including multiple instruction stream, multiple data stream, okay? Then we have a couple of controllers and all of that. So, but when we now talk about the architecture proper, we have to talk about the machine representation of the instruction. Because now we want to play with the instruction. We talked about instruction set architecture, right? So for us to be able to do that, then we'll have to put on the annotation bar. Then we have to talk about how this is represented. Okay, let's change the column. I want to tell how the instruction is represented. How do we also represent data? Okay. Okay. Now, I think in our last lecture, we made mention of a number of examples of, architectures. Okay. The ARM and the likes. Okay. And then we now want to go way into dealing with this. So when we talk about computer instructions, for instance, we say they indicate both the operation to perform and the operand to use, right? So the operand, which we'll see shortly, using model sim to play with some VHDL codes, the operand may come from either the memory, the register, or the instruction itself, okay? And I also don't want you to forget that the computer architecture is more like the programmer's view of the computer, okay? And we refer to that as the instruction set architecture. So we can as well say that it is defined by the instruction set, which is the language, and the operand location. So when we talk about, so now we're talking about the instruction set architecture. We're saying right now that it is defined by the instruction set, which has to do with the language. And then it also has to do with the operand location. And this location could either be in the register or the memory. So in our last class, you all made slides, presentation slides on memory hierarchy, and the likes, okay? So you already know what the registers are, what the types of memory, the cache, and all of those are. Now, but the bottom line is, for us to be able to deal with the instruction set architecture, then we should be able to program all of these. And for us to be able to do that, we will have to represent everything we want to do with zeros and ones. That is where we are going to, okay? That's where we are going to. So we now say that, well, that instructions are encoded in machine language, which are zeros and ones, right? And the programmer, let's say, which you are right now, will therefore represent instructions in some symbolic format called the assembly language, right? And microprocessors are digital systems, as you already know, that can actually read and execute the machine language instructions. So we have the high-level language. Then oftentimes all programmers use the high-level language to develop application programs. And then we use a compiler to convert that high-level language to the assembly language, right? Mind you, we already mentioned something, that the programmer represents all of these digital systems using some symbolic format or representation, symbolic representation, which we call the assembly language. And then we are not saying that with the compiler, we are able to convert the high-level language to this assembly language, okay? So, so technically, before I move on to the next slide, we have the instruction set architecture. sitting on the computer or the computing device. And on this, we have all of your applications, your Windows, we have your high-level languages, your word processing applications and all of those, okay? So this is something like this, but we are interested in this. That is what we want to deal with, okay? And when you look up the notes we already have, then you'll be able to run through quite a couple of things. And now I'd love us to just jump right in. Then I'll make a little introduction, then we'll go into our presentations, okay? Okay. So not too different from all I have said, and now I want to talk about data types and their representation. So, well, you guys already made slides on some of these data types, but in computer systems, we can actually classify, these data types into, say, integer data. And when you program, you use int. Then we have the floating point data, which is usually represented using the IEEE 754 format. And then we have character data, then we have the boolean also, and the instruction format. So we have the opcode, which specifies the operation to be performed. Say we want to perform addition or subtraction, the arithmetic logic activities, we want to load or store. Then the operand itself specifies the data or memory address to be operated on. Okay, and then we have the instruction length, which defines the size of the instruction. So we're going to see this shown in some of the VHDL codes. So it could be, we could say it's 8 bits, it could be 4 bits, it could be 32 bits, and then we now say for us to do that in VHDL, oh no, in VHDL, then we could specify to say in bracket 31, either down to or up to whatsoever 0, okay, things like that. So we're going to see all of those shortly. I'm going to see those in our program as we go by, so like the 16 bits will be 15 down to 0. Then 32 bits will be 31 down to 0. So we see all of those, okay? So what if we have 5 bits, say 5 bits? So in VHDL, we'll specify by 4 down to 0. So, we're taking 0, 1, 2, 3, 4, right? So that's 1, 2, 3, 4, 5. That's what it means. So the bit positions, okay? So 0 is 1, 2, 4. So that's 5 bits. So from 0, taking 0 as 1 bit position to 15 will give us 16 bits. So we're able to specify the instruction length, by using notations in that manner, okay? Then, okay, let's clear this well. So examples of instruction formats, it could be 16 bits opcode, 5 bits for source register, 5 bits for source register 2, 16 bits for the immediate data or address. So we'll see that, how it applies. Now, Want to look at VHDL modeling of basic instruction components. Now, before I move into this, I want to believe you all have model sim running in your systems. Class rep, can I hear from you?
Yes, sir.
You have all installed model sim, right?
Yes, sir.
Okay, perfect. So we are going to be doing some in-class exercises in this class also. So we'll get to that. So just get your system, fired up. Because shortly you are going to be sharing your model sim interface to run this program. We'll walk through it together anyway, nothing to worry about. Okay, go ahead, Jeremiah.
Yes, sir. Sorry, sir. My system is currently faulty, and I don't think I won't be able to use model sim today, sir.
You don't worry. We are going to be calling the groups. So someone in your group should have model sim. So you guys want to interact with yourselves to be sure one person have model sim. And
Sir, thank you.
there's nothing to worry about really. We'll share the person's screen then while we work together, okay? So we'll all make our contributions and effect these codes on the person's system. I have them on my system, but I just need you guys to get busy also. So as you know, we project one of the screens, then some other guys, behind the scene can equally implement those things, and let's see if it will run in your system. You get what I mean?
Yes, sir. Thank you, sir.
And that's what it is. So, because a bulk of the theoretical basis, there are things you can research. So I just want to run through. We'll make presentation. Maybe we'll select one group at random today to make their presentation while we ask questions across all the groups, for grading. Then we'll just move on. Don't worry. I want us to try to make the class as interactive as possible. You already have some resources in the YouTube channel. There are some notes there. The information may not be the same, but they are very useful. We'll mention a few details in those notes and in this class, but the goal this time is to make sure we drive the practical aspects more than we'll drive the theoretical basis. Okay, I saw another hand up. Okay. So VHDL modeling of basic instruction components. So let's assume that the instruction decoder takes a 32-bit machine. Okay, so we want to get busy right now. So I'm sure you may have to document these details, okay? Because once we pull it down, then you may have to, but don't worry. But let's just get going for now, okay? So in this case, we are looking at a particular VHDL code we want to run right now. And you are going to work on this right away, okay? So we want to assume that the instruction decoder takes a 13-bit machine instruction, okay? And extracts the opcode, that is the source registers and immediate value. In our previous slide, okay, that's the code, okay. We made mention of this six bits for opcode, 5 bits for source register 1, 5 bits for source register 2, 16 bits for immediate data or address. This is more like an instruction, format for 32 bits, right? So once we add all of this together, this is 10 plus 6, that's 16 plus 16, that is 32 bits, right? So in this case, this instruction format already splitted the 32 bits into this format. So we're going to use 6 bits for opcode. We're going to use 5 bits for the first register, another 5 bits for the second register. Then we're going to use 16 bits for the immediate data and address, okay? So now let's assume that the instruction decoder takes a 32-bit machine instruction, and then it's going to extract the opcode, the source registers, and immediate address values. That is the instruction input is a 32-bit vector, okay? And well, I know I didn't mention it last time, but I'll just mention it this time. We have data types also in VHDL, okay? So I made mention of the standard logic, right? So when we use the standard logic, we could assign a 0 or a 1. But now we are looking at vectors, okay, for the 32-bit vector, where we can take a string of 32 bits, for instance. So we are now going to use standard logic vector, okay? So in your modeling, oh, no. In your modeling, we are now going to use, recall we made mention of standard underscore logic, right? Last time, but this time is going to be standard std underscore logic underscore vector. Okay, so once we do that, let's assume for this 32 bits, it will be bracket. So it will start from 31 down to 0. So this is how we declare it, okay? So by the time we come to the entity, we want to actually describe the instruction decoder, right? So the entity for the instruction decoder, then the port in the port declaration for the instruction, which is 22 bits, and its input is going to be declared as the instruction. It's going to be declared as, say, instruction. Talking about the port declaration, we said this is input. We'll call them input. Then std logic 31 down to 0 because it is 32-bit vector. Is that clear?
No, sir.
Okay.
No, sir.
No,
No,
sir.
sir.
Okay. Now, you remember in your VHDL activities, last time we made mention of the entity and the architecture, right? Do you
Yes, sir.
remember
Yes.
that? Okay. Now, when we declare the entity, we want to specify the inputs and the output terminals, right? Isn't
Yes,
it?
sir.
And now this particular exercise is telling us that the instruction inputs. So here, our interest is instruction decoder. This is our interest here, instruction decoder. That's what we want to do, okay? That's what we want to program. We are doing, you know, machine representation of data, and we already said, well, this is done by just using zeros and ones, okay? So we are looking at the instruction set architecture itself. So everything we want to do, we have to represent using the machine language. And the machine language is zeros and ones. And we want the hardware, what we want the hardware to do is to understand the zeros and ones. So it means that we are going to assign the critical processes. We are going to assign some zeros and ones to the critical processes that makes up the architecture of the computing device. Okay? So our memory, our registers, our opcodes, and everything is going to take on some predefined value of zeros and ones. Do you understand?
Yes, sir.
So our basis here now of this computing device is the instruction decoder. So we want to design an instruction decoder. So the architecture, let's put it that way, how is the architecture going to look like of this instruction decoder? And we already have the details. So for this instruction decoder, it's going to take a 32-bit machine instruction. Then from that 32 bits, we are going to break the 32 bits down such that the opcode will take some of the bits, the registers will take some of the bits, and the immediate values will take some of the bits, okay? So that it will be 32 bits. So you have 32-bit system, 64-bit this, and all of that. So how did they come about that? That's what we are trying to do right now, okay? How are they able to map those bit activities to the machine components or to the component devices? We know, okay, fine, the memory is supposed to be a physical hardware, okay? So how come the computer understands the memory to be something, to be memory. So probably the computer understands the memory to be 010111110. Probably this is the memory. But for us to be able to say this is the memory in terms of the coding or programming, then it means we have assigned this value. Do you understand? Did you get that? I need to get your feedback before I move on.
No, you said we have assigned which value.
So this is just an assumption, okay? So let's say we have assigned this value to the memory, okay? So we know the memory is localized somewhere, but we want the system to understand that 0101110, once we punch that, it means the memory, okay? So what the machine understands is this. So once the machine sees this, the machine knows this is the memory. Do you get that?
Yes, sir.
Okay. Yeah, so we could also say, well, the opcode, the operation code, or the whatsoever is 010. Okay, so by the time we assign all of those values in that manner, because then we now say fine. So let's assume we want to say for the opcode, we're going to play with that too. So let's assume we have AND, we have subtraction, we have to add all the way, okay? So let's assume we say, well, for this the opcode for AND should be 010, this should be 000, this should be 111, right? So it means that the machine representation of the instruction set architecture as it stands right now is going to understand the opcode for AND is 010, for subtraction is 000, for addition is 111, and for the memory location is 0101110. Do you get that? So if we add all of this together, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, this is 17 bits. So we've actually designed a 17-bit system here. Is that okay? If this is all we have to do? Hello?
Yes, sir.
Yeah, so that's what we're trying to say. So we're saying machine representation of data and instruction. Okay, so these are instructions, okay? These are all instructions. So we want to represent them with data. But in our case, we want to say, well, we want to assume that the instruction decoder is our goal, okay? So we want to assume that it is a 32-bit machine instruction. So for this 32-bit machine instruction, we want to extract the opcode. Some bits from this 32 will go for the opcode. Some bits will go for the registers. Some bits will go for the immediate values. So we are saying that the instruction input is a 32-bit vector, because since it's not just a 0 or 1, we cannot assign it to the simple standard logic. So because this time we are having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So we're having these 32 bits, okay? So it's more than just a single 0 value or a single 1 value. So in your VHDL programming, we are going to assign it as standard logic vector rather than the standard logic. Does that make sense, please?
Yes,
Why
sir.
are we assigning it like that, sir?
These are data types. You recall in your regular high-level programming or whatsoever, where you have to do you've done C++, okay? So you have integer data type, right? Which you specify as int. Then you have let's say your Python, the boolean, which is bool. You have your double, which you use for your floating point. These are data types. Okay, now GABA. Well, don't worry. I think I'll still have to conduct probably we'll have a comprehensive lecture on VHDL where we'll have to talk about the data types and all of that. I'm just pulling them up, based on demand, based on what we want to do, okay? Have I addressed your question?
Yes, sir.
Okay, Gaba Mohammed, please go ahead.
Yeah, sir, why are we assigning binary numbers to the and sub, like
Yeah,
why we
because
assign?
Yeah, because we are doing machine representation of data. So what the machine understands is zeros and ones, right? That's what we, mentioned in our opening, in the introduction. So we say this is a digital computer, right? So in digital computing systems, both instructions and data are represented using binary codes, right? So the binary code, you call it bits, right? But it's actually binary digit, right? Where the B is taken and the it is taken. So that makes it bits, right? Yeah, so what the computing device understands is binary digits, so zeros and ones. And the way data and instructions are represented and processed is critical to computer operations. That's what we mentioned, in our opening. Is that clear?
Yeah, but sir, I think I thought probably the program would do that by itself instead of we manually putting it kind of.
Well, now you don't see this. For the system to understand that, you don't have to do this. Now, when you punch B on your keyboard, what do you see on the display? B, right? So it has already been pre-programmed to take on a particular bit value, which is distinct from A. So all the alphabets on your keyboard right now have some predefined, pre-programmed binary values assigned to them. So this is the actual architecture. That is what you are doing in computer architecture. Is that clear?
Yes, sir. Yes, sir.
Okay, so we are going into the virtual aspect of it. So, but every other guy just picks up the device. Oh, I punch my F. Oh, it displays F. But that's not what the computer understands. You understand F, but the computer understands something else. So that F already have a predefined binary digit assigned to it. That's why you do your ASCII coding and all of those, right? Your gray code, your this, your SS whatsoever, and all of those things. You do them. You must have done ASCII and all of that. So all of those will tell you, okay, fine. The keyboard, these are the standardized binary digits assigned to the keyboard. So that if you want to come up with your computing device prototype, then you have to go follow the standard. Okay, so that when other programs that are made, now have to run on your system, it will run on that platform. Is that clear? Gaba, is that
Yes,
clear?
sir. Yes, sir. Yes, sir.
Yeah. So now we need to bring you back to why you are here. You are here because you want to do the real thing, not just punchy something that everybody sees, but you want to know how it actually works. Okay. So okay, let's move on. Now the opcode output extracts the first. Now we're giving the details. Okay, so the instruction input is a 32-bit vector representing the machine instruction. Now the opcode output is going to extract the first 6 bits, which denote the operation, right? And then we have 2 registers here. Register 1, ROS1 and ROS2 represents the source registers extracted from bits 25 to 21 and 20 to 16 of these long 32 bits. Okay, so we're going to say, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So from 21, 22, 23, 24, 25, the first register takes value. Then from 16 to 20, Then from this 2019, 18, 17, 16, the second register will take on these values, while the first register will take on these values. Then the immediate output extracts the last 16 bits. So we now count the last 16 bits. So then to take that. So which can represent an address or immediate data. So this is just a simple illustration. And then we'll say we have a 32-bit instruction decoding machine. Is that clear? So who's going to give a shot to this? So let's, I think group one made their presentation last time. So let group B, we need someone in group B to project his or her model sim. Don't worry, we are going to be telling you what to do. We'll do it together as a class, okay? Then if it runs on your system, then we are good to go. Okay, so who's going to share his or her system now? Ademoluti, Peter, Hussein, Adeola, David, Esther, Miriam is also here. Okay, the class rep is here. The class rep have, okay, so let us use the class rep system. Oladoko, Miriam, Ajoke, can you share your model sim interface, please? You don't have to get scared or worried. We are going to tell you everything you need to do, okay? So I want you to, I have it on my system already, but I want you guys to do it this time on your own. Okay, let's get going. Share your system, please. Is Miriam here?
Yes, sir. I'm currently launching it.
Okay. Oh, you can share your screen so we see how you launched it. Miriam, can you share your screen so we see how you launched your model sim? Okay. Okay, perfect. So now we're going to do this together. So I would love everybody in class to unmute. If you are not in a noisy environment, please. Just unmute. Unmute your mics. I can see. Then Miriam, you want to even unmute your video right now, if you can. Because you're representing your group. Or better still, everybody in your group should unmute their video so we see this is your group activity right now. But we're going to tell you what to do to make life really easy. So Miriam, we can't hear you. So unmute, please. Miriam, can you hear us? Can Miriam hear us?
Yes, sir. I can hear you, sir.
Yeah, please unmute your mic. Unmute your mic, please.
Okay, sir.
Yeah, so we are going to be interacting now. Now, can everybody in your group unmute their mics also? Yeah, if possible. And Miriam, can you unmute your video?
Sir.
Okay, you can unmute your video. Okay, fine. It's okay. Now, let's just keep things going this way. Now, I want you to go to Jumpstart. Go to Jumpstart. Click on the Jumpstart, please. We want you to be very quick. Please be very fast. We have so much.
Okay, sir.
Okay, so jumpstart. Okay, so you want to create a new project. So create project. So, well, what we want to do here is instruction decoder. So let's type instruction underscore decoder. Instruction underscore decoder, right? Instruction underscore decoder. Okay, so you can okay this. Let's okay it. Okay. Yeah, go ahead, go ahead, go ahead. Then create a new file. So let's also call it instruction underscore decoder. Yeah, just give it the same name, instruction underscore decoder. Okay, so wait, you already hit enter. Okay, well, it's VHDL. So wanted to be sure because oftentimes, well, it's VHDL, but you want to select the right program. Then close this. You can close that. Hit on the close button on the add items. This add items, yeah, yeah, beautiful. Now you're going to double click on the new file, on the design file, double click on it. Yeah, double click. Perfect. So can you expand this? Yeah, expand it. Let's begin our coding. So we're going to add some libraries, okay? So let's add some libraries. So library, so type library space IEEE, then semicolon, not space yet, add a semicolon. Good. Then let's go to the next line. So we are going to use, so type use, IEEE space IEEE. We're going to use IEEE standard logic, IEEE dot std dot logic, no underscore, sorry, not dot, underscore std, sorry, IEEE dot std underscore logic, yes, underscore 1164 64, go ahead, dot all, right? Include a dot, all, yeah, all, not org. We're not doing the website. ALL, right? Yeah, ALL, then semicolon. Now, semicolon. Now, we're also going to be doing arithmetic, and we want to use some unsigned integer. So we're going to also use the IEEE standard logic arithmetic all. So go to the next line. Go to the next line. So use IEEE.std underscore logic, just IEEE.std underscore logic underscore arith. That's ARITH, not array, arithmetic. ARITH dot org. Semicolon. Now, just copy this same library and paste. So we just edit the arith to unsigned. Yeah, so we don't waste our time. So change the arith to unsigned. That's UNSIGNED, right? GNED. Beautiful. So now we've included the basic libraries that we need. But we have instruction as our input, then we have the opcode as our output. The register 1 and register 2 are also output. Then the immediate value is also output, right? So we have a single input, which is instruction. And that instruction is going to take about 32 bits. And then every other output, the opcode, the register 1, register 2, immediate, whatsoever, they are going to, take on specific values as we define. So now let us describe our port activity. So just hit your enter button like twice. Then let's entity. So type entity space. Then now we're going to give the entity a name, right? Okay, so why not use lowercase letter? Okay, it's fine, but we don't have issues with that. It's all the same, but okay, so let's give the entity a name. Let's give the entity a name. Let's give it instruction underscore decoder. That's what we are doing really. Instruction underscore decoder. And you should be very careful, and you should ensure that what you have spelled is what you retain, right? Now we have declared the name is, so space, so is, then go to the next line. Let us define the port. So go to the next line. So hit your tab once, just hit your tab once. So let's make things look a little nice. Good. Okay, let us declare the port. Port. Type your port. You could say cap port or just that. That's fine. Then open the bracket. Open the bracket. Good. So now we have our first input. We have our first input. The first input is instruction, which is 32 bits, right? The instruction input is 32 bits. So type instruction. Then put your full colon, then space. So identify this as input as in, then space. Then we already said this is going to be standard logic vector, right? So you're going to say std underscore logic underscore vector, underscore logic underscore vector. Then open and close the bracket for that. And then in that, have you opened and closed bracket? So you want to be sure. Now you've eliminated your port bracket, right? So after the vector, we need a bracket, open and close. No, not outside that bracket. Now, okay, good. You've done the right thing. So now inside that bracket, we are going to declare the number of bits. So we're going to type 31. Space. Down to. No, the down to is together. No space in between. No space. Yes, space 0. Down to 0. Good. So come out of that bracket. Hit enter. Let's go to the next line. Then your tab. Let's go under instruction to declare our next our output. So we have opcode just under instruction. So type opcode. So we want to define our opcode. So full column, not opcode, OP, operation code, not up down, operation code. Opcode. So So the opcode could be either and, it could be subtraction, it could be anything. Okay, so the opcode, full column, yeah, so declare it as the output, space, output, space. Now, every other guy on your model sim, you could be doing the same thing because I could just tell you to share your screen. Let's see your output, okay? We could do the wave thing on your own system, okay? So I just want you guys to get comfortable playing with all of these things on your own. Okay, now that's fine. Output, so space. So we're also going to declare this as the data type is also standard logic vector because the opcode is going to take about 6 bits from our illustration. So you're going to repeat, so you can as well copy the standard underscore logic underscore vector down to, just copy all of that then. Down to, highlight it to the down to, okay, you would have just highlighted all. Okay. So this time is 6 bits. So that will be 5 down to 0, right? So now I want you to shift your bracket. So let the bracket be very close to your, yeah, let's just keep to convention. Yeah, perfect. So let's go to the next line. Semicolon, please. Include semicolon after the first and the second. Okay, yeah. Else our code will not run. Yeah. So let us go to the next line and declare the other output. We have the RS1, the register 1 and register 2, right? So RS1, you could say capital, okay, either small letter or capital letter. Let's use cap letter RS1. Yeah, so we know it's register 1. So we're declaring this as our output. So do the same thing, the full column. Then output, declared as output. It's also standard logic because it's taking on 5 bits. So let's declare a standard logic vector. So let's declare it as 5 bits. Good. Then semicolon, then go to the next. So you can as well copy this and just change the RS1 to RS2, right? Perfect. So let us declare the immediate value. So say immediate, the last output. So you can just copy that entire line, just paste. That's after the bracket. Yeah, okay. Yeah, after the semicolon. Perfect. So let's declare our final output immediate. Just paste that and change the RS2 to immediate instead of typing and typing. Just paste. Good. So change RS2 or RS1 to immediate. Then this is also output. Then how many bits is this taking? 16 bits. It's taking the last 16 bits. So we're going to change the 5 to 15, right? So 15 down to 0. Okay. So yeah, close the brackets. That's now before the same. Now let that semicolon go after the bracket, after the second bracket. Yes. Then end the entity by declaring end the entity name. Go to the next line. Yeah, end. No. No, go back to this. Still go back. No, go back. Yeah, then hit enter. End entity name, end instruction, end space, instruction underscore decoder. So you don't make mistake, just copy that name and repaste it, right? So you are sure it's the same thing you're typing. Then semicolon. So you can leave about 2 spaces, hit your enter bar like twice, you know. Okay, so let us declare architecture. So type architecture. So we're going to give our architecture a name. So what name should we give to it? Well, I just use Bevora, but you could use anything. So probably instruct decoder or instruct underscore decode or whatsoever in capital letter, just to distinguish, you know, whatsoever you want to call it. So you can call it. So let's be quick. We are running out of time. Decoder, okay, underscore instruction, or whatsoever you want to call it, it's fine. So we have given the architecture name, but we are going to link it up with the entity, so space of the entity name. Of. So we are saying this architecture is of the entity name, that entity name.
I want to write the entity with it.
Yeah, no, just the name of the entity.
Just the name.
Yeah. Just the name, yeah, of the entity. Then is, space, is, then hit enter, then type begin. So we use port to declare entity, so we use begin to declare architecture. So enter, go to the next line. Well, you can leave begin there, just take it back, take your begin back so that we take the process forward, okay? Okay, then tab, hit your tab. So let's define the process. The process here is instruction. Say process, in then bracket open and close, then in that bracket write instruction. Process. Yeah, so want to describe the process, then in that type instruction. Well, use capital I, so let's distinguish this a bit. So use capital I for the instruction. For I, yeah, cap I, yeah, let's then underneath that, underneath the process, type another begin. No underscore, please. Clean the underscore, then hit enter, then go under the process, type begin. So we want to define the process. So we're going to describe this process and also end the process, right? So we already started the process with instruction begin, then hit enter. Hit enter. So under that begin, you can tab like twice if you want to. Then let us define the opcode. So opcode. So that opcode you wrote, ensure the character, ensure your no spelling error, right? Opcode, so less than is give a little space, then less than equal to. Give a little space. Instruction. So the instruction that is in the process, right? Make sure it is the same spelling with that instruction in the process. So in bracket open and close, this is going to take from 31 down to 26. 31 down to 26. Okay. Then semicolon to end that, then go down. Or you can just copy that opcode whatsoever. So we just edit the ROS1, ROS1 immediate. Okay, yeah, so we don't waste too much of our time. Okay, so that's going to be ROS1, less than or equal to instruction. But now this is going to take 25 down to 21. 25 down to 21. Then the ROS2, a semicolon, please. Include a semicolon. Then ROS2. Then that's going to take 20 to 16, right? 20 down to 16, that's what we said, down to 16. Then semicolon, then the immediate, which is also our last output. So that's going to take from 15 to 0, right? From 15 to 0. So when we declare 16, when we declare 32 bits, so the first 16 bits will be used as the data and the address, then all the way. Then the last set of bits will be used as the opcode. So we want to end process. So go to the process line underneath and end the process. So you want to tab once, right? No, tab once. No, not yet. So tab, yeah. So end process. Then semicolon. Then you want to end the architecture. So you end, so now you can end the architecture. So end the architecture with the architecture name, right? And don't forget, it should be the same spelling with the decoder underscore instruction, right? So you just want to copy it so you don't, no spelling error. Then semicolon. Perfect, and semicolon. So now you want to save. Either you hit your Control S or you come hit the save button up here. Okay, Jeremiah, go ahead. Can see your hand up.
So the opcode, it has 5 bits. It's showing 5 down to 0, but in the note that I gave us, it says 6 bits.
And yeah, we are just playing with things here. We're just
Okay.
playing, yeah, we're just playing with stuff. Yeah.
I'm thinking that maybe it will come to an error because in the architecture is 31 to 26. So that's 6.
31 to 26, yeah. Then that is 25 to 21, 20 to 16, and then 15 to 0. Yeah.
All right, so.
Yeah. So we have 31 to 26, then from 25 to 21, then 20 to 16, then 0 to 15. Yeah. It's okay. It's okay. So if we take it from this, from the bottom, 0 to 15, 16 to 20, 21 to 25, then 26 to 31. So that's 32 bits, right? So we didn't skip anyone, right? So save. You can save. Have you saved? Have you saved, Miriam? Okay.
Yes, sir. I've
I can
saved it.
see, and I can see the save button. Then come to this file name, the design file where we have a question mark. So right click on it. Is it right click or right click? Yeah, right click. Just right click on that line. Right click, then compile. Go to compile. Let's see if it will compile. Then compile selected. Compile selected. Hit that. Let's see if it will compile. Boom, you have 2 errors. So what did you do wrongly? Okay, so let us go back and begin to trace. Now, all of those U's, turn them to lowercase U's. Our architecture turn into lowercase architecture. Let us see. Lowercase, let's then go to U's for the libraries. Let's turn them to lowercase, turn them to lowercase. No, STD, yeah. Now, okay, just hold on, then save again. Save again. Then try to compile. Let's see if it will compile. Selected. Okay, we still have 3 errors. The library, entity, instruction.
Brackets after begin.
No. You don't need to. You don't have to. You don't have to. You don't have to. Okay.
Of the answer.
So let us track what you're doing. Okay. Now, immediate, okay, correct. Then RS1, RS2. Okay, Corey, they tell us. Go ahead, please.
So I think because I remember when we were explaining this thing, you said that the opcode is meant to take 5 bits, but yeah, it's taking 6.
Okay. That's
And
not,
in the part of ATC, say 6.
I don't think that's the issue.
Okay, sir.
5 to 0, right? That's 6, yeah, it's okay. Yeah, I don't think that's
Sir,
not
Jeremiah has something in the chat.
okay. Now STD, yeah. Okay, so we need to track where the error is. Instruction underscore decoder. That's instruction. Okay. Now your port is lowercase I, so turn it to uppercase instruction. The I. Yeah, turn it to uppercase, then yeah. So save and let's compile. Let's see. Save and let's so compile, let's see. Still did not compile, right? Okay, then the instruction, inputs, that's outputs, standard underscore logic vector. Semicolon, 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 yeah.
Sir,
Go ahead.
Jeremiah said semicolon after the process instruction.
No. You don't have to. You don't have to. Okay, so now less than equal to after the last bracket immediate. Which is that?
The one before the port. Before we close the old port bracket.
Yeah. No. Not before, it should be after. So what did you do wrongly? Well, we'll trace it, nothing to worry about. Okay. That is library IEEE. Okay, that's that.
Now that we change the ports to
Okay,
uppercase instruction, are you not going to change the
now ROS1, ROS4 is 4 to 0, 4 to 0. ROS2 is 4 to 0. Yeah, so save. Then compile.
That's fine.
Can you compile now? Right click and compile.
Yes, sir.
Yeah.
It's showing successful.
Successful, yeah. So that was it. So it was bit allocation mismatch, right? So you assigned more bits than we declared. You added additional 2 bits. So if that was going to run, then we're going to probably increase this to 33 to down to 0. Is that clear? Hello, is that clear now?
Yes, sir.
Yes, sir.
Yeah, so we posed a little problem. Miriam gave us a little problem to solve, right? And that is that. So it means the code is up and running and we are fine. So meaning at 32 bits, there's no single mismatch. So we did not declare beyond what we did not assign beyond what we declared. Okay, so we assigned beyond what was declared, so it didn't run. So now the program just ran. So let us hit the library and let us see how this works. So click on the library. So you see underneath, yeah, go down, then click on the library, yeah. Beside the project. Can you do that? Yeah. Click on it. Let us go to the library. Yeah, go to your work directory. Click on the positive sign on the work directory. Okay. Can you do that quickly? Our time is running. Someone needs to present shortly. Click on the positive sign, just to your left, just beside the work, the drop down. Yes, yeah, no, that's work. The first directory there, just right, you are not right clicking, just click, no, the drop down, the positive sign, click on the positive box. You see a positive box beside your work directory.
Yes, I've done that.
Yeah, so you have just one. No, just double click on it. Double click on so you've not done any work till date. This is your first project. So double click on it.
Yes, sir.
Yeah, double click. Double click on that file, on the simulation, on that decoder. Have you double clicked?
Yes, sir.
Is it opening?
Yes, sir.
Okay, so let's wait for it to open. Good. So that's what we have now. So now you are going to right click on the you are going to right click, just right click on the file name, the one that is highlighted, the instruction underscore decoder. Right click on it. Right click. No, the highlighted.
Yes, I've done that.
No, right click. Yeah, right click. So there's going to be a drop down.
Yes.
Yeah, then go to add wave. Add wave. Click on the add wave. Have you added wave? Okay, so let us see your wave. Is it loading or add wave?
It's loading.
Perfect. So we have this now. So you should be able to assign the input. So let's right click on the input instruction decoder. Right click on that. No. On the wave, we have 1, 2, 3, 4 stuff open. You are not going to, don't come to your left. We have a list of items. So we want to assign the inputs, right? So right click on instruction underscore decoder in the wave. Can you do that? Miriam, are you still with us? Yeah, right click.
Yes.
So right click on that, on the instruction. Yeah, right click. Have you right clicked on it?
Yes, sir.
So go to force. Let's force it. No, force. Click on it. Then assign just assign 32 bits, a long chain of bits, right? So in the value, go to the value. So you're going to remove that value. No, value. Yeah. So delete what you have there, select all and delete it. Have you done that? Or you can just delete everything,
Yes, I've deleted everything.
So you're going to assign zeros and ones in 32-bit position, not 32. Don't type 32. Just you're going to type a long list. So you are going to be counting, probably 0, 1, 0, 0, 0, whichever way, but make sure it's 32. 32 bits. Is that up to 32 bits?
Yes, sir. 32.
Okay, 32. Then hit OK. Okay. Have you done that?
Sir.
Okay, so I think the system is dragging. Okay, now go to simulate. So you're going to go up. You see where you see 100 PS? Just after 100 PS, then click on the simulate button. The toolbar, go to the toolbar. The first line of the toolbar, just under where, no, toolbar. You know where you have file, edit, and all the next line? Just move down.
Yes, sir.
So you see 100 PS, not there. No, go forward. No. Under that line, the next line. Remove the drop down. Pull out of the drop down. Yeah, on that line. Keep moving your cursor to the right. Just be moving your cursor to the right. Keep moving. Yeah, no. After that, the next button. Keep moving. Yes, that's simulate. No, behind that, before that. No, before that. No, you are going too far. Yes. So run. That's the run button, right? Run. So run. Let us see. Boom. We have it done, right? Isn't it? So we have it assigned, right?
Yes, sir.
Good. So you have your system running now. So that's fine. So how do you feel about this, Miriam? Miriam, we need to get your feedback. How do you feel about this process that you achieved your first VHDL code?
Exciting, sir.
Oh, okay, that's fine. So I want to believe it's also exciting for the entire class. So, okay, now I think I will just share my slide.
Sir.
So I'll share my slide again, then we'll run through a few things. There's so much to do, but we are constrained by time. Okay. Yeah. So I'm going to resume. Yeah. So this is what you just did, right? This is the code you just played with. Now we have another code here, which is to implement an arithmetic logic operation decoder in VHDL. It's much the same like what you did. So we just declared the libraries. We're also using the same set of libraries. And then in this case, we have the opcode taking on the data type standard underscore logic vector, and we are assigning 6 bits to it. Then the arithmetic logic operation is going to take another 2 bits, right? So with this, we now have to begin. We are using case here. Most of you that do programming, you know how to go about that. It's more like we are running a loop, right? So if we get this, when we get this declaration 0, 0, 0, 0, 0, well, I want the arithmetic logic operation to be add. So when we get this, so it's more like a loop, right? So when we get this declaration, then we want and. So it means. You have any question, please?
Please, only seen the first page, sir. Sorry.
What's that?
It's the first page that we are seeing.
Is the what?
First page.
The first page, really?
Yes, sir.
Machine representation of
That's your
instruction
presentation slide.
Can you see my presentation slide now?
Still the same thing. Yeah, we can see the presentation, but just that page.
Okay, let me share it.
Yeah, just
This one. Can you see it now? Is it visible now? Okay.
Okay, now you can see your cursor moving. Oh
Okay.
yeah.
Okay. So, okay. Is visible now?
Yes, sir. I think so.
Yeah, in HD.
Okay.
It's okay now.
Okay, perfect. So sorry for that. So now we are implementing the arithmetic logic. So, but what are we driving at here? It's machine representation of instruction and data. So it means that whatsoever instruction we want the computing device to perform, we can actually assign a binary value to it. Does that make sense at all? I need your feedback, please. I need you to talk to me. Does that make sense?
Yes, sir.
Okay. So now we
So I
have.
didn't get that last sentence, sir.
I said the idea is that we are talking about machine representation of instruction and data. So the idea is whatsoever instruction we want the computing device to perform, a binary value has to be assigned to it. Is that clear?
Yes, sir.
So in the design process, we are taking you as the programmer this time, but you've been so comfortable programming softwares, but now we're saying, well, this is the hardware programming, okay? We want our hardware devices to perform certain operations, and then this is what we want you to do, okay? So I think that's what it is. So in this case, so we have the entity. This is more like an arithmetic logic decoder. So the opcode, we've defined it to have 6 bits, and the arithmetic logic operation to have 3 bits. So now we have declared the entity where we have the input and output defined. Then the architecture is defined. So we have the process, which is the opcode, right? So the opcode operation is such that, recall that we assigned it to be 6 bits, but now we want to map the 6 bits to 3 bits, okay? So that when we assign a 0006 bits, then we want that to tell the arithmetic logic operation to perform AND. And we know the arithmetic logic operation is to take on 3 bits. So it's going to map this to 000, okay? So the last 3 bits, and that will be AND. So once we initiate a 000, the opcode operation is going to be add. Then for 001 is going to subtract. Then for 010 is going to be the AND operation, the OR operation, the exclusive operation. And then when we get any other value other than this, otherwise, then more like your if statement, say else, after you've declared your if answer, you say, well, if everything in the if loop or whatsoever is not seen, then else, then no operation, right? Then we close the case. Then we end the process, then we end the behavior, which is the architecture, okay? So that's that. So this is supposed to be class interaction. Why is it necessary to decode instructions in digital computers? And how does the instruction format impact performance? So I will do that right now. Then we'll call one of our groups to present for another 5 minutes. So this is class interaction. I want to get someone from each group. Okay, well, I'll call you guys at random. Arowolo David Oluwatosin. I want you to throw your thoughts on this. Why is it necessary to decode instructions in digital computing devices? And how does the instruction format impact performance? Can you tell us? Okay, Arowolo is absent in class, so we'll mark him out of our class today. Is Arowolo David Oluwatosin in class? Okay, he's not in class. Okay. Gaba Mohammed Abubakar. I think I know you're in class. Gaba, can we hear you talk to this?
Yes, sir. Yes, sir.
Okay, so tell us, why is it necessary to decode instructions in digital devices? And how does the instruction format impact performance?
I think it's crucial because it plays a vital role in understanding what operations the CPU should perform.
Okay.
So it helps the CPU to navigate to know, okay, this is to follow the instruction, or let's say how it should go about the operation of the computer in general.
Okay, brilliant. Now,
then for the performance, it's by doing that, it's increased the efficiency, I think.
Okay.
Yeah.
Okay.
Because it makes the CPU to probably have a clear path to follow to be able to perform those instructions.
Okay. Brilliant. That's fine. So do we have Joseph Oluwatomiwa Ayomide in class? Okay. Fidelis Emmanuel Toby?
Yes, sir. I'm in class, sir.
Okay. So please, are you using device?
Sir?
Yeah, okay, fine. It's better now. Can you share, just tell us a little about this, your views?
So I think instructions, it is necessary to decode instructions in digital computer because it allows the CPU it enables it to be able to execute binary commands so that the software can run on the hardware. And also the instruction format impacts performance in the sense that it helps to improve performance by reducing the time to interpret instructions. That's what I understand.
Okay, that's fine. So I'll just go to a little highlight here. So the key points, which you guys covered is that, decoding instruction is essential for the CPU to understand what operation needs to be performed, right? So that for us to know what the CPU has to do, then decoding instruction, is essential, okay? And here we also have that a well-optimized instruction format can reduce the complexity of the coding process, and that will improve or enhance the CPU speed, okay? And if you look at your reduced instruction set computing architecture, simpler and fixed length instructions definitely lead to faster decoding, right? So we're looking at optimized performance, right? Okay, which you guys mentioned. That's perfect. So you're doing well. So this is supposed to be in-class exercise where you're supposed to implement a VHDL code to represent a simple instruction set with two operations: load opcode and store opcode. Can you take this? So you're going to do this as an assignment, and then God willing, in our next class, we'll call on anybody at random to push this up, and then let's see how you were able to play with it, okay? It's supposed to be in class, but we already played with one in class, so we'll just make this an assignment. So you want to take this as an assignment, okay? So do I have further instruction on that? No, okay. So you're going to take this as an assignment, which is supposed to be in class. It's just a simple short code, but you want to implement a VHDL code to represent a simple instruction set with two operations. So the two operations here are the load and store, okay? So the opcode for the load is given, and the opcode for the store is also given. So that's one. Then have you taken this already? So I want to move to the next. Have you taken this?
Yes, sir.
Okay, so that's the code, but let's move to the next. So this is the next exercise, which we are supposed to do also, but you are going to also take this. So you are going to implement this also, and then I would love the class rep to compress. Once you implement it in model scene, Then you save them, you transfer the codes to a Word document, include your details, your matriculation number, your name, your details and all, and then compress them in a single folder. Through your class rep, you should get to me latest Tuesday, okay? So I'm going to assess that as part of your assignment for the week. Okay, then it's going to be graded. So well, I wouldn't want you guys to share ideas on this. I want you to do it alone, okay? Let's see how far you understand what we're doing. So if you're able to resolve these two assignments on your own, then it means you are really getting very comfortable playing with VHDL. The more you practice, the better you become, okay? So we're not trying to cheat the process this time. We just want you to build your capacity, okay? Who knows? You may end up becoming an instruction set architecture programmer in one of the leading organizations, or better still, set up your own organization and get these things going. Probably just from, one of these lectures, we never know, you never know. So you want to feel a little comfortable doing it yourself, okay? So you're not trying to rely on someone else's strength this time. So let's come to what we talked about in class, and then you try to play with that. So I think that is that for now. So if you've picked this up, then I think I'll just pull down my slide. Well, I'm going to upload the video. So when I upload the video, I already swiped through the answer to the first exercise. So you may be able to play with that. But this second, the solution is just after this slide. So I won't swipe any further so that you play with it. So in our next class, we may come back to it if it's necessary, So, but I should get your feedback latest Tuesday. So any question for now? Any question for now? Any question? Okay, so let's go to our in-class presentation. So we won't be taking everybody today. So we'll take group 7. So group 7, project your slide and let's get your presentation before we call it a day. Group 7, please.
Come on, let's have it.
Let's have it.
So share your slide, please. Group 7.
Sure, we are coming, sir.
Okay. Well, our time is ticking, so it's like you're not ready. Okay, I think I know what to do. So let's.
So our laptop is lagging, sir. Please hold on, sir.
Okay, so well, I'm also trying to help from my end. So. Okay, so I think I'll just share. So I'm sure this is your slide, right? So you can begin your presentation. Is anybody from group 4? Okay, they are not ready. So let's just pull them out.
Yeah. So
So you don't have to worry. Let's okay, group 4. Someone from group 4 should project, please. Group 4. Let's grade group 7. Group 7 didn't show up.
sir, we are here, sir. I can start now, sir.
Okay. If group 7 is here, okay, fine. Go ahead.
So help me with the next slide, sir.
I think you are in charge, right? So you want to go on.
Okay, sir.
I'm sure we can all hear you. So just do your thing. So I'll give you about 7 minutes, so we could ask some questions.
All right, sir.
To the very best.
So introduction to data representation. So data representation is it refers to the way data is stored and processed at the machine level. So since the language the computer understands is just 0 and 1, so there are ways to represent this data on the computer. And so next slide, sir. So we have the integer representation, we have the floating point representation, we have fixed point representation. So I will be starting with the integer representation. So the integer representation is just the way of representing whole numbers, which can be positive, negative, or 0. So just whole numbers. So the floating point representation, it allows for representation of wide range of values by storing the numbers in a format that includes a sign, exponent, and antecedent. So the floating point representation allows us to represent large data, like large values. Yes, large values. So we have it in next lesson, please. Okay. The IEEE 754 standard is a standard.
You seem to be the only person presenting. How about your colleagues?
Yes, sir. We shared the slide, sir.
Okay, go ahead, please.
Okay, so the IEEE standard is the standard. Yeah, the standard for representation of floating point numbers. So it was adopted in the year 1985 and revised in the year 2008. So, and it was developed to facilitate the portability of programs from one processor to another and to encourage the development of sophisticated and numerically oriented programs. So, next slide, sir. Next slide, sir. So the fixed point arithmetic, unlike the floating point arithmetic, where the point can float from one point to another, but in the fixed point arithmetic, is just a numerical representation method used in computing to handle real numbers with a fixed number of digits after the decimal point. So it's unlike the floating point arithmetic, where the decimal point can float from one point to another to to accommodate a wide range of values. So fixed point representation maintains a constant position for the decimal points. Next slide, sir. So we have the application of fixed point arithmetic. So we use it in DSP, that's digital signal processing, where speed is essential. We use it in robotics and control systems where hardware constraints limit computational resources. So the benefit of fixed point arithmetic provides an efficient alternative to floating points. Yeah, so it's very efficient compared to the floating point arithmetic. Next slide, sir. So I would like to stop here so that the next person can continue, sir.
Good morning, sir.
Good morning. Well, you're with the class. Good morning, everyone.
Good morning, everyone. Good morning, everyone. So this is Colade presenting. So I'll be talking on overflow detection and management. So overflow detection and management is actually a critical aspect of computer arithmetic when we are particularly talking about integer operations. And it occurs when an arithmetic operation produces a result that exceeds either the maximum or the minimum limit, which can be represented by the data type used by the programmer. And it leads to incorrect calculations. So we have different types. We have the positive overflow, which is when the result gotten is too large. We also have the negative overflow, which is when the result is so small. And we now have some management techniques, which are highlighted, like saturation arithmetic, modular operations, and its importance. Importance is just simply makes our result to be reliable and safe. So next, I'm going to advanced binary management. So advanced binary management is just it encompasses the various techniques for performing multiplication and division of binary numbers efficiently. And we use two significant algorithms in this this domain, which are both the Booth's algorithm for multiplication and the use of carry look-ahead adders for addition. So I'll go straight into the multiplication in binary arithmetics. So a technique used here is shift and add method, which essentially encompasses us with shifting and adding based on the binary representation of the numbers, as well as Booth's algorithm. Booth's algorithm first has different stages. We have the initialization stage, we have the bit analysis stage, we have the iteration stage, and we also get the final result. So to touch on this briefly, the initialization stage, the algorithm initializes the two registers, one for the multiplicand, which can be represented by M, and one for the multiplier. And the bit analysis, for bit analysis, what happens is that the algorithm first examines the least significant bit in the multiplier. If it is 0, it performs a right shift. And if it is 1, it adds the multiplicand to the accumulator and performs a right shift. Now, division in binary arithmetic. Some methods highlighted here are shift and subtract methods and restoring and non-restoring division. And we use it in division operations in processors, especially in the ALU design. I've already talked on both algorithms and so carry look-ahead adders. So now, fast algorithms. A brief overview of fast algorithm is essentially like both algorithm and carry look-ahead adders, just that it's designed for fast arithmetic operations. And it matters because it's essentially in applications requiring high-speed calculations, such as real-time processing and complex simulations. Some real-world applications of this include digital signal processing, cryptography, and scientific computing. And these are some of our references, sir. Thank you for reading.
Okay. That's okay. So we'll now ask a few questions, right?
Yes, sir.
Okay. Okay. Now, how do we represent floating point numbers in a computing device? Now, if anybody from your group cannot attempt that, then we want to talk to someone in.
So
5.
Sir, I'm here, sir.
Go ahead, please.
Okay, so we represent a number. If I didn't get the question, sir.
So I only asked how we represent floating point numbers in computing devices.
Okay, so we have a whole number, then the decimal point, then the exponent, sir. So the significance is the whole number.
Okay.
And
So I think what I expect you to say is that, well, we do the representation using scientific notations, right?
yeah, yes, sir, yes, sir.
So that's in binary, it could be in sign bit, exponent, then we have mantissa, which is fractional,
Yes.
right?
Yes, sir. Yes, sir.
Okay. Okay, that's fine. Nice presentation. Then I need someone in group 5. Someone in group 5 to attempt this question. Okay. So do we have group 5 with us? I just want someone to answer with the voice note. Anybody from group 5? We have a Bafemi Moses.
Yes, sir.
Okay. Now, we just played with a VHDL code where we made mention of immediate, right? Immediate, operand or something there about. So what do you understand by that word immediate operand? Okay. Can anybody help, Okay. So,
The opposite.
Immediate operand is like they are like values that directly specify the instruction of the program.
okay. Can you give us more details, please?
Okay, for example, instead of pointing to a memory location where the data is stored, we can the operand itself provides the data itself within the instruction, something like that.
So it means it's a constant value, right? Encoded directly within the instruction. So there's no reference to the memory address. Okay, I think we are good to go. You guys are conducting your review. So we expect the submission for the 3rd week before our next class, and your in-class exercise, we just turned in-class assignment as submission from everybody latest Tuesday. So any question, please, before we call it a day? Was the class informative in any way?
Yes, sir.
Okay.
Yes, sir. Very much.
Okay, so I wish you guys the very best. We see you in our next class. Bye for now.
Thank you, sir. Bye-bye, sir.
Have a nice